Hi everyone. So in this video, we're going to be talking about Booleans. We'll discover what a Boolean is and how Boolean variables can represent true or false values, and then look at a couple different operators that we have to combine Booleans together into complex logical statements. We'll look at the and, or, and not operators, and then see how they combine in an order of operations, sort of like PEMDAS, if you remember that from algebra class. Finally, we'll look at one other special rule related to Boolean logic, and then talk a little bit about how this applies to programming. So to get us started, let's talk about Boolean logic and what exactly a Boolean value is. So most of the variables that we create in programs are related to numbers or text. However, sometimes we need to store information that isn't really clearly a number or text. And in the previous videos, we looked at a couple ways we could store some esoteric data formats, very complex pieces of information. But sometimes we just have very simple questions, things we want a yes or no answer to. While we could use text or numbers to represent this, and in fact, that's what old programming languages used to do. We could say, okay, well, we have yes and no. Maybe 1 is yes and 0 is no. Maybe the word true is yes. Maybe the word false is no. This isn't a very flexible way to solve this problem. We kind of have the opposite of what we had in our other situations. In the other situations, the information was much richer than numbers or text. So we had to find a way to break it down into numeric or textual pieces. With Booleans, these yes or no questions, this is actually too much. Numbers have other values besides 0 and 1. Text has a million different words we could put down. So numbers could end up being misused. We could accidentally do math to them. Text could end up having a typo. And both of these are going to use up way more space than what we need, which is really just one single binary digit. Our Boolean piece of data here is a yes or no, an on or an off. We just need a binary 1 or 0 for this, not an entire integer that could be thousands large, not a string of text that could hold a sentence or paragraphs. So to solve this, programmers actually created a third primitive type of value, a third literal value we can put in our programs, and that is what is called a Boolean. So in a little bit, we'll look at how Booleans get used in programming, sort of where they come from. But before we do that, I want to talk a little bit about this name Boolean, where it comes from, and sort of some stuff that's not purely programming related. And that is going to be our concept of Boolean algebra. So this name Boolean comes from a logician named George Boole. It's literally his last name turned into a category descriptor. Boolean is from George Boole. So he was around in Victorian era England, and actually he was one of the teachers of Ada Lovelace, who we've talked about previously. What Boole wanted to do in some of his research was create a language for thinking about the truth. And he wanted this to behave almost like mathematics, where in language, our normal descriptive language, there's a lot of fuzziness around what words mean, and so sometimes the truth is a gray area. He wanted something that was rigidly true or false, and some scientific way to apply some rules to these true and false values in order to have a guaranteed perfect true or false answer at the end of your transformations. And so from this, he devised this concept of Boolean algebra. And in Boolean algebra, we start with two basic values, true or false. These values might represent the truthiness of a statement. That's what he had envisioned. a statement like the sky is blue evaluates to true. And his thinking was that this would be operating on premises like that. But it might also be the answer to a yes or no question. Might be, is there space left on my computer hard drive? Yes or no. True if there is, false if there's not. It could even be related to the presence or absence of energy or a material. It could be, is the spacebar currently held down? Is there energy, electricity firing through that little circuit? True for yes, false for no. So this Boolean algebra starts with these two values, true and false. Then it adds operators, operations that let us combine these symbols together. So if you remember in algebra class, this name operator is what we use for addition, subtraction, multiplication, division. That little X sign is your multiplication operator. The plus is your addition operator. So in Boolean algebra, we actually have a completely different set of operators. Minus doesn't make sense. What is true minus false? Instead, in Boolean logic, our operations are and, or, and not. And if you remember that Boole originally thought about these as applying to sentences, then you can kind of see the intuition of how these different operators are going to be used. And is going to let us combine two things in a conjunctive statement. It's going to say, well, is this part true and is that part true? Or is going to let us kind of create choices, and not is going to kind of flip things. So the way that Boolean logic is built up is that we build a Boolean expression by chaining together these Boolean values, true or false, with these operators and, or not, to create complex true or false expressions. And then, as that name algebra would suggest, we can simplify those expressions using our basic rules to arrive at a single final value, a true or false, that is the answer for the entire complex thing we've constructed. So this is just like simplifying an expression in algebra. And what I want to do first is introduce the formal rules of our three operators here, and, or, and not. So let's start off with and. So and is in some ways the simplest tool for combining together Boolean values. So and is going to take a very similar role to the one it does in language, which is it's going to combine two different Boolean values, and the answer is only going to be true if every part of the inputs are true. So say we've got P and Q. We've got a variable P, we've got a variable Q. To make it easy, let's think about it in the terms Boole did. The example I always like to use for and is the sentence is, it is sunny and it is rainy. So P will be it's sunny, Q will be it's rainy. The condition to see a rainbow in the sky is that it must be sunny and it must be rainy. So if we were going to look at that in Boolean logic, we could represent that as P and Q for it's sunny and it's rainy. And if we want to see that rainbow, then it has to be that both of these pieces are true. This it's sunny needs to be true, and the it's rainy needs to be true. And this little graph I've created here is what's called a truth table. It shows us a nice, neat visual way to read these inputs and see what the result will be. So for our and here, we can see my P could be true or false. So this column is when P is true. This column is when P is false. Same thing with Q. Here it is when it's true. Here it is when it's false. And so Remember, we had said we're only going to see the rainbow when P is true and Q is also true. It needs to be sunny and it needs to be rainy. So the answer in this box here is that yes, we would see one when both of the inputs are true. But if it's not sunny, if it's actually nighttime, then even if it's raining, there will be no rainbow. If it is not rainy, if it's just a plain old sunny day, then even if the sun is shining, there will be no rainbow. And finally, if it is a nighttime, somewhere clear weather, then there's no chance at all. There's multiple things that are wrong. So we can see in our AND operator here, the only way to get a true answer for two Boolean values is if both of them are true. Everything else, every other combination leads us to false. This AND operator is really great when we want to strictly guard a total truth. We don't want any half-truths slipping in there. This AND is great for saying, okay, every part of these multiple conditions must be met. And in logic, we often represent this AND rather than writing out the word AND with an ampersand or an upward-facing caret like this. So if you see any of those in relation to Boolean logic, that's just what they mean. There are other ways of writing AND. But this is our first operator, the thing that lets us create a conjunction of multiple premises. Say this thing is true and that thing is also true. So now let's contrast that with our next operator, OR. So OR is going to work a lot like AND, where we've got a P, we've got a Q, and we're doing P or Q. And these variables could be whatever name we want. But what OR is going to do is give us a union of different possibilities. It's going to say, well, this part could be right, or that part could be right. They could even both be right, but some piece of this is correct. So the example I always like to use on this one is schoolwork, where you have options. Say, oh, well, for this test, you either need to get an 80% or higher, or you need to have handed in every homework. And if everyone in the class does that, we get a pizza party. In that case, if everyone did well on the test, say that's our P, if it is true everyone got above an 80%, then there would be a pizza party, no matter how they did on Q. So in this true column for our P, everything is true. Same thing, if every single student handed in their homework and that guarantees a pizza party, then as long as they've done that, everything in this row, this was the homework handed in Q, that is also true. What that means is if P is true and Q is false, or Q is true and P is false, we actually still get a true answer. And there's only one way we could end up at false with our OR operator. And that is if every single condition is not met, this one isn't met, and that one also isn't met, then you had multiple chances, none of them worked out, the pizza party is canceled, and the class weeps. So this OR is sort of the opposite of our AND. It's great for when we have different choices that could all satisfy a requirement. So the other thing to note is that OR is sometimes represented with a pipe or with a downward facing caret. So if you see those, still the same thing. That is our OR operator. The last one I want to look at is NOT. And if you notice, the truth table on NOT looks a little bit different. And that is because NOT doesn't work with two things. And OR works sort of like our normal algebraic operators, where they go right between two things. We saw P or Q, P and Q. With NOT, it is a unary operator. It is applied to one single thing, sort of like an exponent in algebra. In our case, the NOT is a prefix right before a variable. And this is the operation of negation. Just like in plain language, if you say not, you're reversing whatever comes after. If I say it is not sunny, then I'm saying, well, it's the opposite of that. It's actually rainy or dark or some other thing. If I say, oh, well, it's not 7 a.m., it could be any other time, but it is definitely not that one. And so in Boolean logic, what our not does is it reverses whatever was in that Boolean variable. So if P was true, then not P is false. If P was false, then not P is true. And this negation is useful when we can't think of a clear way to phrase a question, but we definitely have the ability to think about the opposite. Not gives us the tool to flip things, reverse them, process them into a form that we can actually handle. And it's actually kind of, in some ways, the most useful of all these operators because it lets us use our and our or in very creative ways. So this not here is our third basic operation. Like our others, it does have some symbolic representations. Sometimes you'll see an exclamation point or a little notch like this, a line that comes down. Those, if you see them, that's just other ways to write not. So now we've got our operations. Next thing I want to talk about is, well, what are the rules for combining these? Much like in algebra, we have an order of operations that helps us think about grouping and simplifying Boolean logic. The first one of these rules is just like in math class, you can put parentheses around any part of your expression, and that says do that part first. If you've ever wondered why parentheses always comes at the beginning of the order of operations, it's because it's literally the symbol that says, well, I'm going to break the normal rules. So obviously that needs to happen first, or you can't break any rules that come before it. So for us, those parentheses are going to work exactly the same way here in Boolean logic. If I put parentheses around something, like let's say this part of our expression here, that says start with that part and then follow our normal rules inside of there. Otherwise, the general rule in most programming languages is we start with the nots, then we do the ands, and then we do the ors, and each one of those goes left to right. So if we had a large complicated expression like this one here, then we're going to say there are parentheses. That's definitely going to be what we do first. Then we're going to look inside these parentheses and say, okay, our highest precedence thing is a not. Is there a not? And yes, there is one right here. So the first simplification we make is say, well, not true. That's the same as false. So we can simplify and then rewrite the expression just like we did in math class. And now we've got this not true and false. And so this is still parentheses, so it's still going to come first. So true and false. We know from our truth tables that and is only true if every part of it is true, and this part here is false now. So we know that inside those parentheses, that whole thing is just going to be false. Now, we've got one thing in the parentheses, they can fall off. We don't really need them anymore. Now we have to look at what to do next. And so we go back to our normal rules and start with not again in this bigger expression. And we say, okay, well, there is a not. So not false turns to true. And then we're out of nots. So let's start with ands, left to right, true and false again. So it's going to turn that side into false. Now the ands are all gone. And now we've got our ors. So there's one or left, false or true. Or works as long as any part of it is true. This right part is true. So our final answer, if we were simplifying this expression, would be that this whole big mess up here becomes just the value true. And that is the answer for that logical statement. So this shows you how Boolean algebra ends up working. It is a way for us to chain together complex questions saying, gives us the tool to express things that we might not have any computer function, anything that gives us exactly the answer we want. But if we can piece it together from parts that we do have, then we can arrive at one final true or false answer. And the great thing is the computer does all of this for us. We don't have to handwrite out these simplification steps. In our program, we would write something like this very top line here, where instead of trues or falses, we'd probably call functions or do tests. And then the computer will simplify down to just a yes or no answer at the very end. So that shows us our order of operations and how we simplify. There is one quick little thing I want to call out. So Boolean logic, there are literally entire college courses dedicated to studying it and all of the rules, just like how algebra has rules like the rule of associativity and commutativity and distribution. There are similar rules in Boolean logic. A lot of them will look very familiar to you if you have any background in algebra. There is one, however, that trips people up all the time. And so I want to talk about that one specifically. And that is De Morgan's rule. So De Morgan's rule is the rule for how we distribute a not over parentheses. So that term distribute, if you remember, it's us saying, well, I've got something in parentheses, a term like this, and I've got this thing on the outside right next to the parentheses, and I want to apply it to everything inside. So you see this in math class when there's multiplication right next to parentheses, and it's like 3 times the quantity 2 plus 3. The way you do that in mathematics is 2 times 3 plus 3 times. So you take that 3 and multiply everything inside. So people try to apply similar thinking to Boolean logic and say, oh, well, this not, I can apply it to everything inside the parentheses, say not P and not Q. But De Morgan's rule actually works a little bit different. It says that when you're doing Boolean logic, if you distribute a not over parentheses, you actually have to change what operator you're using. So not P and Q actually turns into not P or not Q. Notice the and turned into an or. And if we think about this, again, using real life premises, then that makes a little bit of sense. Say, my premise that I have, my statement here is, I do not have to wake up early if it is not snowing and it is not a weekend. Or rather, I do not have to wake up early when it is a sunny day or, it is a weekend. I can sleep in on those times. So if that is my P and my Q, then I don't have to wake up early when either one of those is not met. What that means is I don't have to wake up early when it is not a weekend or it is not snowing. If either one of those is true, then I don't have to scrape off my car to get ready to go to work, because you don't work on weekends and you don't work on, or you don't have scraping your car if there's no weather. So in this case, you can see here, what before, if you state it positively, is and every condition needs to be met. If you try to distribute that not out, then any condition can break this original one. By distributing out the not, we've turned it from, well, all parts of it have to be true, that I don't have to wake up early if this and that and that and that, becomes, well, I don't have to wake up early if it's not this, or it's not that, or it's not that. It actually flips it around. Or to use our rainbow example again, there will not be a rainbow when it is dark and cloudy. So if any one of those conditions is not met, we don't have a rainbow because it's not sunny and raining, then either it's not sunny or it's not raining. You need one part of that to be met. And it's the same thing with our or. Not P or Q becomes not P and not Q. If we know that it is false, this whole thing here, P or Q, then that means the only way that this whole thing ended up false was if this part was false and that part was also false. So when we distribute out the not, we end up with not P and not Q because every single part of this had to be false to negate the whole thing. So that is one thing to keep in mind when you start writing programs that use Boolean operators, is if you're manipulating things around, saying, oh, well, I have functions that give me the opposite of what I need, or you see a bunch of nots and you're trying to draw them out. This actually works in both directions. You can factor out the same way we could pull out common factors in math, pull that not to the front. When you do that, you have to be careful with your ands and your ors because ands and ors flip when we're distributing knots. So that is De Morgan's rule. It is the one thing that always trips people up when they're doing Boolean logic. But hopefully, if you keep that in mind, you can manipulate your expressions without accidentally causing a bug in your programs. So the last thing I want to talk about in this video is why it is that we even care about this in computer science. So in computer science, there's sort of two ways we end up with Booleans. The first is we do direct comparison of variables. So you actually can use the symbols greater than, less than, or equal to, which in most programming languages, equal to actually uses two equals, because if you remember, one equals is already used for assignment, so we can't use it for that. But that lets us directly compare values. It would be valid for me to write in a Python program, my variable equals 3 greater than 4. So 3 is obviously not greater than 4, but what that line would be saying is test is 3 greater than 4, and give me a yes or no. So my variable, after that assignment occurred, would hold the answer to that, which is just the value false. And we can use these comparators, these operators that take two variables and give us a yes or no, to compare all sorts of things. We can use it to figure out numbers being greater than or less than. With text in some programming languages, it even tells you which comes alphabetically first. And some languages even let you override it for more complex types, like photos or music or any other abstract representation, any object you might want to compare. But that is one way that we get Booleans, is by directly comparing two variables or two literal values. The other way is from functions. There are a lot of functions in programming languages that give us back a yes or no answer. For example, if I have a variable that has a string, then my string variable has a function attached to it, much like the example that we saw previously. This starts with function is actually part of a string. So if you want to use it, you would do my string dot starts with, but this function takes in one parameter, something that you think should be at the start of that string. And if we think about what this function gives us back, it wouldn't make sense to give us back text because we already know the text. We already know the whole string. We already know the piece we're looking for. Wouldn't make sense really to give us back a number because there's only two choices. So what the starts with function is actually going to give us back is a true or false value. And so in Python, there's literally two keywords added to the language, the word true and the word false. And you can use those keywords outside of a string. There's no quotes because they're not text. and use that to represent one of these true or false values. And a lot of functions, especially related to string comparison, especially when you're working with files, there's functions to check, does this file exist on the computer? Or do you have permission to do this thing? Are you connected to the internet? Each one of those questions you might want to ask the computer has some function representing that feature that will return to you a true or false value. And once we know that, we can chain together complex statements from a bunch of these functions to test for different conditions in our program. Things like checking, does this file exist? And do I have permission to open it? And does its name match the name I'm looking for? If all of those are met, then I will do something in my program. And that's really how Booleans end up being used in programming, is using them to check the status of the system or to evaluate inputs that come from a user or from a file to test that your information is what you expect, or to let a user make a choice and then react differently depending on the result. So we're going to have several videos coming up where we look at that a little bit more deeply, but hopefully this gives you just a taste of this Boolean logic and the ways that it will be useful for us when we are writing our programs. So that is our introduction to Booleans, and I'll catch you all in the next video.